I'd like also to thank the organizing committee and the sponsors. Okay, so I'm really happy to share a few, probably about 25 minutes about our work we have been doing recently on how we can recycle plastic, waste plastic. So it's probably not a polymer material or mostly material chemist. Okay, perfect. Thank you. So what I will try to do is that just giving you some hints on what we do and how we can recycle polymers to make added value fuels or chemicals, but also advanced functional materials. Okay, so first, just to tell you a few words where I'm coming from. I'm coming from the north of France. I work at this Institute of Electronics, Microelectronics and Nanotechnology. It's quite a big institute, about 500 people, including, of course, researchers, engineers, postdocs, and PhD students, among other visitors. So it's here in the north of France. It's one of the five here technological platforms in France. As you can see here, the different departments are, everything is centered around nanostructures and macrostructures for going from nanosystems, optoelectronics, telecommunication, and acoustics. So we're the only group actually working on chemistry, mostly because we are actually half chemists, half biologists. So we try to use materials, but also technology to design sensors, but also other different materials for various applications. Among those, I can cite indeed nanoparticles, polymeric nanoparticles, but also other nanostructures for bio applications. Here you can see antiviral. No, this is antimicrobial, antiviral, but also we apply this nanotechnology in aquaculture. And the bottom part here, it's mostly related to energy, environment, and different aspects of catalysis and sensing. Plastic, I think, like everything, if we talk about plastic, and particularly during COVID, I think everybody has been using plastic, gloves, masks, wearings, and everything. The big problem is not the plastic itself, it's the access to many plastic and the fact we produce a lot of plastic, but we don't recycle the plastic. And this plastic often ends up in water, and that indeed has harmful on the living species. And when you look at this figure also, the fabrication of plastic generates about 3.4% of overall global greenhouse gas. And this is exactly the same amount as the full aviation generates per year. It means when we deal with plastic, you generate a lot of CO2, but other greenhouse gases. So the ideal indeed is not to stop fully producing plastic, but at least to recycle as much as we can of the plastic we produce over time. But unfortunately, what you can see here, the recycling is only never exceeds 11 or 12%. Yeah, this is typically what I said. I mean, of course, you know that plastic in our daily lives, I mean, the best example is here, and mostly we'll talk about PET, but also you find it everywhere around us, in our clothes, in our food, and everywhere. So, but yet, it's the big problem is the waste of the management of the plastic, which impacts everything living species, whether in poor countries, developing countries, or even the developed countries, as I will show in the next slide. So, when you look at this, it's how so far the plastic is managed. Most of the time, a lot of countries, they do just a landfilling. You see it's probably mostly between 70 and 80% of the way to manage the plastic waste. But when you look, it's only this green, the recycled, you see it's everywhere. Whether you're in Africa, you're in India, you're in China, the States, or in Canada, it's roughly the same, exactly the same amount of recycling. Nothing is better even in the developing countries. The only thing which is different between the developing and the developed countries is the mismanagement. Of course, you have a better management of plastic in the developing countries than in under or developing countries, okay? I took this example, which is quite recent, on plastic. This, you see, it's about a year and a half now, how indeed the plastic can impact the living species. These are copypods. Copypods or planktonic species, it's what the fish larvae eat to grow. It means this is the food, it's like milk for babies or the food for us. So fish larvae, they will eat these planktonic species in the real world and then they grow. However, if these planktonic species are exposed to the macroplastic, what they do, you see they ingest the macroplastic. They can even generate nanoplastic. You can see it here. And unfortunately, of course, they don't die. But now, when the fish larvae will eat this planktonic species, they will also eat the plastic. It means you end up with fish potentially that actually has plastic in the body. And there are so many demonstrations showing indeed that the fish have a lot of macroplastic, unfortunately, in their body. So back to I would say the most viable methods used for plastic management. Certainly the easiest one, I think most of the country will do, it's in 80%, it's the landfilling. You just drill holes and you fill in with the plastic. Unfortunately, this way you don't recycle the plastic, you don't make any use of the plastic, and potentially over time, the plastic will release some harmful species through the degradation, which will end up in the soil, in the water, and of course will have negative impact on the living species. The other way of doing is recycling, mechanical recycling. And this indeed, people make with these composite materials at the industrial level, and particularly in the construction. So this is really something which is very useful, although it's really low added value. Now, there is another, this I think you have seen everywhere, it's the incineration. You just burn it up. Either you burn it up and then you capture the energy, you can reuse it, or you just burn it up and generate CO2. Unfortunately, that's exactly often what's happening. Mostly now, as a chemist, I will focus on these two methods, the chemical re-upcycling and the functional upcycling. And particularly this functional upcycling, because it's a recent method, it's simple, but also it allows to make functional materials out of something which is called waste, okay? So this is the typical examples you can find. You see what you did when we talk about functional upcycling. It means you just functionalize, you modify the surface of the material, okay? Through other polymers, it could be small molecules, it could be metal nanoparticles, it could be anything. And then you actually bring a functionality to the material. And from a waste, you can now generate something that has a functional, it means something you can use in real life, okay? As an adsorbent, it could be food packaging, because you can also put here molecules or polymers, they have antibacterial, antiviral. It could be a catalyst, so you can see the diversity of the things you can do on the surface of polymer through the well-known chemistry or polymer chemistry. Okay, so I will start with the first example. We have been actually performed with a group in Tomsk Polytechnic University in Russia. So we took the PET. The PET is just the plastic bottle here you have in your hands. Then what we did, it just actually hydrolyzed the polymer, and if you know, I will briefly tell you exactly what you can do. Then you generate this molecule, and if you add salt, you can generate a MOF. MOF, if you know what MOF is, it's metal organic frameworks. There was a Nobel Prize awarded in 2025 in chemistry for the MOF preparation, okay? That's something. Then the MOF, of course, we can, with a laser, just treating with a laser, we can make a zirconium carbide graphenic type of material just on the polymer, which is initially actually nothing else than meant for being waste. So here it's exactly for a chemist how you do. When you hydrolyze the PET, you generate this terephthalic acid and ethylene glycol. So this is one actually of the initial ligands for making MOFs. Okay, so if you add any salt from transition metals, or you end up with making with these very nice and crystalline materials called metal organic frameworks. Yeah, this is, you can see, if you could just look at recent, you see, well, the Nobel Prize in chemistry for these 3 scientists indeed on MOF. So what are the advantages of MOFs? MOFs are cheap, they're highly porous material, they have thermal stability, and stable to hydrolysis, and extremely versatile for different applications. Because they're porous material, you can use them for storage, for instance, but they are also used for catalysis because they feature transition metals and, among others, biomedical applications, okay? So what we took the plastic, we hydrolyzed it, we optimized the conditions. It was in sulfuric acid at 75 degrees C. So we looked exactly how we can generate the most actually important amount or density of acids on the surface. And what we find, the optimized conditions are really 75 degrees C, and the hydrolysis time, it's 5 minutes. When you do this, then you add this zirconium salt, you end up with having a zirconium MOF on the plastic surface. This is, you can see here, it's just in imaging and chemical imaging. This is the zirconium on the carbon. You can also look at the UVVs here. You can see from the initial plastic, which is hydrolyzed, to the one with the MOF, you see there is an appearance here of a small hint here. It's just a small bump due to this MOF absorption. Okay? We performed all the characterization to be sure, indeed, with XPS. You find the carbon and the zirconium and oxygen all coming from the MOF. And specifically here, what you see, you have an sp2 carbon. It means it's really the carbonic from the, this phenyl group from the acid. Zirconium is also present with a different chemical surrounding, so it means definitely you have been able to form this MOF on the surface. Then what we did, so we have the plastic MOF, and then we just took a small laser, light emitting diode laser, which is very cheap. You can buy this for a few tens of euros from China. But of course, the problem is just you're limited by the power. You only have 1.6 watt. So what you can do, you have 2 parameters you can play with, the power and the depth. And you can write directly on the MOF. You can transform the MOF directly to carbon zirconium carbide. The reason why you have zirconium, because the MOF, the initial MOF was based on zirconium. If I take iron or take any other things, of course, this will be different. And on top of it, because you use the carbon and you use a laser, you generate also graphene. So you see, you can make from a waste something which is a functional materials, and it's very easy and simple. You can pattern, because it's a laser, so you can write any pattern I want, very simply, without any efforts. These are just the characterization. Now, when you look here at what's happening indeed, that is the initial zirconium becomes mostly zirconium carbon and zirconium oxygen carbon bonds. So you see, you start with something which is about a few microns, and you end up with 145 microns here. The nice thing about this, you can tell me what you can do. You see, we started with something which is completely transparent or almost transparent, and we end up which is completely a black matter. You can see here, if it's a black matter, it means it absorbs the light from the UV to the near infrared. But most importantly, now, if I irradiate this material, I generate heat. It means I can capture photons and generate heat. And that's what you call a photothermal material. What are the applications of photothermal materials? There are many applications. You can use it for, like, to make just a patch for treating infections on your skin, but also you can use it for desalination or for environmental application, okay? So what you can see is just by any light emitting diode, but it could be also exposed to you have the same absorption as the sun. So if you expose this material to the sun, you can generate heat, you see, and you can reach up to 70 degrees C probably in a few minutes. So we looked indeed at the mechanical stability of the film. Now, if it's really mechanically, if it can really stand a lot of heat, here we just took sand and we rotate this in a cylinder for 24 hours, and we look at indeed the morphology. At least there's nothing changing on the surface of the material. The same for the photothermal. Here after the test, before and after the test, there's nothing happening. The same as also the sheet resistance. It means we have something which is mechanically and chemically stable on the plastic waste. Now I give a second example. It's related to the energy, how we can recycle plastic waste into electrode materials for energy storage. Just brief introduction about energy storage. I'm not sure indeed if you're very familiar or not, but I will give you just the simple, this is what you call a capacitor. This is a supercapacitor. Supercapacitor is just you increase the area, okay, of the energy for storing much more charges, okay? This is what you buy. When you look now at how you can do this to make a supercapacitor, you have indeed to enhance the capacitance through the surface area, but also the applied voltage. So if you increase the voltage and the capacitance, then of course you enhance the energy storage of the material. The way to do it, you make new materials as electrode, but also you play with what you call the electrolyte. Instead of using water, you're limited to 1.23 volt. You can use organic or polymer-based or gels electrolytes. Okay? So, the ideal indeed to make a supercapacitor, if you can have something which has a high conductivity, but when you make porous material, forcingly you lose somehow a little bit of the conductivity, high surface area, something that resists to the corrosion because you use an electrolyte here in between, high thermal stability if you want to operate at high or low temperature, especially at high temperature, and also controlled size distribution. It means you have to design a material that has here a porous structure, but also the pores should actually have the size which is higher than whether it's the anion or the cation, then they can diffuse inside and then be stored within the porous layer. Otherwise, they just remain on the surface, and forcingly, there's no point to make that way anymore the porous material. Biocompatible, it will be also compatible with composite materials, not expensive, and biocompatible, it means now I make something if I can, just as a waste, it will be degraded in nature without any causing harm to the environment. Okay, so these are the different electrolytes you use. Aqueous, it's green, forcingly, but the problem is you're limited by the small voltage. As I said, well, the energy you store, it's square directly linear to the square of the applied voltage. So it's really quite small. And the reason, of course, then when you use water, if you go a little bit too high, you have either oxygen evolution or hydrogen evolution, depending, we have what you call water electrolysis. So this is really not the way you can reach a high energy using supercapacitors. You can use non-aqueous, organic, but the problem, you can reach up to 3.5 volts, but you have to keep really very low the water content, which is not easy, especially for some polar solvents, so you can always capture some water. So the ideal here is the ionic liquids, but again, they also have their own problems because it's very viscous as well. So the motion or the diffusion of ions is quite limited. But so the ideal is to make indeed what you call all solid supercapacitor. It means you have polymer gel instead of having these organic or water-based electrolytes. So again, what we did previously, I said we used a laser-based light LED, laser. Here now we use the CO2 laser. Why CO2 laser? Because it's much faster, you can write, but also you have much higher power. And with the CO2 laser, you can see I can write when I'm saying any polymer, it could be even a potato peel, I can transform that to graphene. It's so simple. If you have just a CO2 laser, you take any polymer, and specifically if you have waste, you can go and write graphene. So I can transform a polymer waste to a graphene-based or graphene-like material. It's quite fast. I can pattern in a single step. It's low cost. It's also tunable. It's very easy. So the first thing we did, this is Dr. Min Li, who is my former PhD student now. She's an associate professor in China. So she took, you have glass here, you have polyethylene film. Just with a laser, you can pattern very easily. You see, you transform the polyethylene to graphene. It's black, it's a graphene type. Then we just actually coat with a spin coating with PDMS, a thin film of PDMS, peel off. Then you transfer this pattern to the PDMS. Now you have a flexible electrode material, okay? So I go from a polymer, a waste polymer, to an electrode material which is flexible, which I can use also for energy storage, okay? You can see the flexibility here. Of course, you can So you can stretch it, you can bend it, and there's absolutely nothing happening to this film. It's quite stable. So just a few characterization, like always. You see, definitely from polyethylene I actually transform that to graphenic type. You can see the graphenic band in the Raman spectrum. This is related to defects. The defects, because you use CO2 and air forcingly oxidize at the same time, you form the graphene, you also oxidize the film. Importantly, you have sp2 types. It means you have some, it's really graphenic with some sp3 and carbon oxygen because you oxidize slightly the surface, okay? Here just some SCM images showing the thickness of this transferred laser-induced graphene with a porous structure. It's important to have a porous structure because then you have a high surface area, and that you can indeed have much higher available surface to store the charges. This, you don't have to look all the details. We can discuss in any, if you need, of course, to discuss the details. But what's the most important thing, it's the stability and the bending. You see, I can bend this electrode for over than 1,000 cycles without losing the energy storage performance. Of course, you can improve the density of the electron density and the power density of this by doping, combining with other type of materials. But what's important is really you have something which is flexible and stable over time. So you can put some of these devices in series or in parallel. You can see if you charge them, then I can release the energy. I can also operate here a calculator for a few minutes. So it means I have made from polyethylene I made an electrode material that is useful to store energy and release this energy to actually power a calculator. Of course, it's not meant because it's a small electrode material. It's not meant for operating a car or something else, but it's really for small devices, okay? Now, what we did with this technique, I can show you this is more really technological aspect. We can also use this technique through a mask. Then we can spray coating here to spray coating, which is very simple and easy technique. You can produce at a much larger, at industrial scale, devices and electrodes. So that's exactly what I want to show you here. Now you take Maxine, it's again a 2D material, it's a new 2D material, and if you can make an ink, then I can spray it on this and I can make as many different features. You can see whatever you want, any type of feature I want, and also I can make as many as I want of these devices. This technique indeed is just very simple, and you can scale up at the industrial level to make any type of the flexible supercapacitors. Now I have the last example, and I will stop here. I think I'm at almost 23, 3 minutes. I think it's okay. Previously, what we did with the plastic, if you remember, we hydrolyzed it. So this acid, we used it to make MOFs, and then we transformed the MOF with a laser. Now, what I want to do is to use this ethylene glycol as a chemical and replace the oxygen evolution here. I will oxidize it and make formic acid out of it. So, you know, if you work in electrocatalysis and water splitting, that's exactly, or hydrogen, if you want to generate hydrogen, what we do, you have a catalyst here and here, you have water, you apply a voltage, then you have hydrogen evolution at the cathode, and you have oxygen evolution at the anode. However, in this type of electrolyzers, and of course you have them actually at industrial scale to generate hydrogen, this oxygen, it's not useful. You do nothing with it. It's released. Probably you can use it in the hospitals, but most of the time it's just released and it's gone in the air. So now the idea, if we can use and oxidize this ethylene glycol to formic acid, then we generate fuel here and another fuel here. One is a gas, the other one is a liquid. So we can generate from one electrolyzer 2 different fuels. Okay? And of course recycled plastic, because this will come from recycled plastic. So, and on top, we want to work, instead of using fresh water, which is also very, especially for countries like Algeria, if you want to generate hydrogen at a larger industrial scale, you don't want to use the water you drink, because we don't have enough already for us and for the agriculture, irrigation. The ideal is to work with a seawater. And seawater, actually, we have a lot over the world. It's about 97.5%. But it's very challenging to work with seawater because you have, of course, in terms of the alkaline of the anode, you have a competitive reaction, but also you have a corrosion of the electrocatalyst. Like anything in sodium chloride is not stable. And on top of that, yes, it's really, you have a lot of dissolved cations or bacteria, microorganisms that can potentially actually absorb on your electrode surface and contaminate your electrode surface. So what we did here, we hydrolyzed the PET, and we took the ethylene glycol, we oxidized it to formic acid, and on the cathode, we generate hydrogen from just the seawater, a reduction, okay? Why formic acid? Formic acid is something which is used a lot of in industry. You can textiles, leather, and rubber production, but also for energy because you have what you call the direct formic acid fuel cells. As formic acid is produced chemically at high temperature and high pressure using methanol or carbon monoxide here, or oxidation of methanol or formaldehyde here. But you operate often at 150 to 200 degrees C and 1 to 2 bar pressure. By producing that electrochemically will occur at room temperature, and also because it comes from ethylene glycol that actually originate from waste plastic, then I think we quite, yeah, it's very nice and approach this way. So here what I want to show you is just we can make in the lab catalyst at almost quite a big scale. It's not proof of concept of 1 by 1 square centimeter, but it's 30 by 20. Easy, simple. And then we apply this. I'm not going to go all through the characterization, but I want to show you is that this catalyst is very actually stable and performant, even much better than the commercially developed catalyst, which is based on ruthenium oxide, to actually oxidize ethylene glycol to formic acid. And this is over 120 hours, which is quite resistant and very stable over time. So that's just, we have checked that with a NMR to be sure that indeed from the ethylene glycol, we get only formic acid. And we have a high Faradic efficiency. It's over 90%, which is quite very high. So then we couple the two electrodes and we make an electrolyzer, one to generate hydrogen, and the other one for formic acid. Okay, so, and we power that with sunlight, so we have really something which is quite a green process using sunlight, but also seawater and plastic waste to generate two fuels. I think that's probably now what we're working. It's instead of generating here hydrogen from water, we use CO2, then we generate formic acid from CO2 and formic acid from plastic waste ethylene glycol. The idea is to generate one fuel from two different waste, CO2 and plastic. And it works very nicely with Faradic efficiency. If you sum up the two, about 160%, which is quite and very nice performance. Now, just I will conclude on this part. When you deal with polymers, it's always the question, is it worth or not to recycle waste plastic? The answer is no. If the process is it's consuming much energy, it means it's more expensive than the initial waste itself, then there's no, economically it's not viable. No industry will go and recycle plastic if the plastic recycled does have less value than the initial ones. So that's certainly the question you should actually, before you recycle any plastic, you should take into consideration. Now, there are a lot of opportunities, especially for functional upcycling of materials, because you only deal with the surface. When you deal with the surface, it means I can only change the surface properties and can turn a plastic waste into functional materials that can be used in packaging, that could be as an adsorbent, that could be used in different areas as well in biomedical application. So this is really, there are a lot of opportunities there, but also because there is a lot of knowledge based on organic chemistry, polymer chemistry, and surface chemistry we can transfer and apply for various and different polymers, okay? That's, of course, there are a lot of, I'm not going to go through, a lot of open questions. And I just would like to thank all the funding agency we have benefited from over the years for doing this work indeed. And then I'll thank the people actually involved in this work. Not all of them, but most of them. I'm not doing an experiment. And I would like to thank you for your attention, and I will be happy to answer any questions if you have. Thank you for your attention.